Oh yeah, you can see me now. Okay, so today's lecture is about the math behind the lighting results. So basically, we're going to do calculations to show you how we derive foot candles or how we determine the number of luminaires necessary to properly light a space. I like to talk about, this is a science lab course, okay? And to give you an example, suppose we wanted to send a rocket to the moon. And we looked up at the moon and we were able to calculate the distance from the Earth to the moon. We determined how much rocket fuel we would need. We determined how fast the rocket was going to go. We determined how fast the moon was moving, right? Because we could take measurements at night and see all of that. We would do all of that, light the rocket, we would miss every single time. Every single time we would miss. A couple of reasons for that. Number one, our point of observation was compromised. We're looking at the moon from the Earth, as opposed to looking at the moon from above the Earth and the moon. The Earth's movement and the moon's movement are in concert together. They're moving like this. So there's no one object that's stationary and the other one is moving around it. That's not the way it's happening. But our point of observation is compromised because we can't see it. Mathematically, we could figure it out. Okay, and when they sent the first Apollo astronauts to the moon, they did figure it out. They figured out the motion of the Earth, the speed of the Earth, and the speed of the moon, and the position of the moon, and they were able to land properly on the moon itself. So in a science lab, we have to be concerned about our point of observation. We have to be concerned about what kind of mathematical equations we can formulate in order to prove that our assumptions are correct. All right? And so today is the culmination of all of that. And I want to, if I point this towards the blackboard there, you can see the first thing we're going to talk about are these three measurements. One, if you see at the top, it's my primitive example of a light bulb. Okay, and what we're going to do is we're going to measure the number of foot candles directly underneath that light bulb. And then we're going to say, I don't want to know about what's directly under the light bulb. I want to know from this angle what the foot candles might be in this position. And the third measurement we're going to look at is, instead of the flat plane here, we're going to look at the vertical plane and say, what are the foot candles on the vertical plane? That's what today's lecture is going to try and demonstrate to you. We're also going to look then at how all of those measurements can be incorporated into a room like this. And then I'm going to introduce you to the software that actually does it. But before we get to the software portion, we're going to do the manual calculations. So I sent everybody today or yesterday some preliminary worksheets that we're going to work on together. And the one that looks like this is actually quiz number 6. And we're going to work it together. As long as we work it together, I can give you a grade of 10 out of 10. All right. But before we get to that, I wanted to review a couple of things that were not clear in the last couple of episodes. And one of them is this IP code. the International Protection Marketing Group sometimes interpreted as ingress protection, IP, meaning that how well is the fixture insulated from penetration of different substances, whether those be powders, whether those be airborne contaminants, whether those be water or liquid molecules. And so the code the first number is the degree of penetration. So IP2 would be lots of things can get inside of the fixture, like your finger. Okay. IP3, maybe the screwdriver. Maybe IP4 is a smaller object, but IP5 would be very difficult to penetrate. So IP, what we're looking for when we're talking about liquids is an IP65 rating. Okay? The 6 stands for what kind of liquids can penetrate under what pressure, 1 atmosphere of pressure, 3 atmospheres of pressure, et cetera. Can everything be submerged? Well, that's the second letter there. So IP65 would allow us to shoot a hose at a fixture and not penetrate. But if we wanted to put something underwater, we'd have to have like an IP68 rating. Pretty simple. Okay, so here they are. IP6. Dust type. No ingress of dust. Complete protection against contact. Dust type. A vacuum must be applied. Test duration of up to 8 hours based on air. The second number is the liquid penetration. I want to get this right. So, if an IP6 and then is followed by a 1, it means that it will resist dripping water. IP62 would mean it would resist dipping water when tilted at a 15-degree angle. Okay, IP63, we can spray the fixture. IP64, we can splash the fixture. And IP65, you can see there, water jets, water projected by a nozzle, 6.3 millimeters against an enclosure from any direction, have no harmful effects. Okay, test duration 1 minute per square meter for at least 3 minutes. Okay, water volume 12.5 liters per minute. Pressure at 30 kPa at a distance of 3 meters. IP66 now, water projected in powerful jets. And okay. IP68. Immersion 1 meter or more in depth. You can actually put the luminaire in a pool that's a 1 meter deep, and it would resist any water coming in. What? The pool lights? Pool lights would be something that would have to be an IP68 rating. However, if it's a deep pool, if it's at the bottom of a pool, we may have to go higher. So that rating has to go higher. And typically, a pool light will be a low voltage light, not a line voltage. Okay, so those are the IP. You'll see those designations on some of the next week we're going to be doing a fixture review of cut sheets. And we're going to do the software, and you're going to see how all of that information is available to you on the cut sheet, so the IP rating is important to understand. Right? And that's all for that one. I sent you this in today's email, and it is a list of Greek letters that we're going to be using. But I wanted to make sure that all of you have a copy of this, so you don't have to write all this down. It's in your email. But the first letter you're going to identify is the Greek letter iota, and that's the symbol for it. And it stands for lumens intensity. And lumens intensity is measured in candelas or candle power, and the abbreviation is CD. We'll see that on some of the cut sheets. The next letter is the Greek letter phi, and that stands for luminous flux, or lumens as we've been using, and the abbreviation is LM. The next letter looks like a P, but it is actually the letter rho. And it stands for reflectance, and reflectance is always presented as a percentage. So how much light falls on a surface compared to how much light comes off of that surface is represented as a percentage. So if we have a surface that will absorb 10%, we would have 90% reflectance, right? That's the way that would work. Then the Greek letter mu, luminous excidence, we'll talk about what that means, and that's lumens per square foot. And then, of course, the Greek letter lambda, which stands for luminance, and that's candelas per square foot. That's typically the amount of light that enters your eye. Okay, you have all that. And now we can begin today's formal lecture. Module 6, photometry. PowerPoint is running into problems. Slideshow from the beginning. So module 6 is called metrics, photometry, calculations, and rendering. And here's our objectives. We'll be able to describe 6 key metrics for quantifying light together with your units. I just gave you a preview of those metrics. Identify different photometry methods for light sources and luminaires. Describe how to read a photometric report. Analyze the lumen method and the point method for calculating the lumens. And then we're going to be able to compare the usefulness of photometric reports, software visualization capabilities as tools when designing building systems. All right. So, photometry is older than Way back when, in the 1700s, people knew that they had to measure how much light and what the effects of light was. They didn't know the nature of light at that point. They didn't know anything about photons. But they knew light existed, and they knew that there needed to be a mathematical equation that could predict how much intensity of light there would be. So all, how should I put it, all physical science, engineering disciplines requires quantification. We need to be able to measure things. So photometry is measurement. Metrics and measurements are important for us to evaluate, and we can compare different lighting effects if we have metrics that we all agree to. So the Illuminating Engineering Society was created in 1906 to formalize what the metrics would be. So we had to all agree that we were going to use the same set of terminology and techniques in order to have consistency in the way we calculated things. So lighting calculations are primarily used for prediction or validation of design. And we can do that manually, or we can do it with computer calculations. Now, truthfully, nobody does it manually anymore. It's all done by computer, and I will show you that. But first, we have to understand the principles of the manual calculation, which is what we're going to discuss today. So, there you see the IES manual called Lighting Science, Measurement of Light, the Science of Photometry. Metrology is the science of measurement. Radiometry is the measurement of optical radiation. Photometry is the measurement of radiation accounting for human vision. Photo, photons, they're all connected. They're all using the same root in language. So just as the satellite radiometry and optical radiation are measured in watts or joules, photometric measurements account for human vision using human luminous efficiency function, V for lambda, discussed in Module 1. The original formulation dates back to 1924. And here are those symbols again. So, luminous flux, appreciation lumen. Luminous intensity, candela, candle power, sorry. Illuminance is either lumens per square foot, which is a foot candle, which we talked about, or lumens per square meter, which is lux. Okay, and it's 10.9 lux equals 1 foot candle. So there's a relationship between the two. So if you multiply lux by 10.7 or 8 or whatever it is, you'll get close to what the foot candles are. Reflectance, that Greek letter rho, we're going to talk about that and see that on our cut sheets today, is represented as a percentage. And luminous excitance is lumens per square foot, or lumens per square meter. And luminance is candelas per square foot, or candelas per square meter. Questions on the quiz on that will come from that slide. Now, we use a variety of devices to do all of these measurements. Remember I talked about point of observation? Well, in order for us to shoot that rocket to the moon, we can't just rely on human eyes. We have to develop instruments that can measure more finite distances. Okay? And here are all of the equipment that we have designed in order to figure out what the heck is going on. There's something called a spectrometer. There's something called a calibrated radiometer. Now, we don't use a lot of these in the everyday Okay, but they're there. I have examples of a light meter here, which I've demonstrated before, and a spectrometer, which this device is here. If I turned it on, which I'm not going to do, but if I turn this thing on, I would be able to tell you the color temperature of the luminaires in this room. Beyond that, we're going to show you examples of the goniometer and the, let's see here, where's the other one? Oh, there's a watt meter. We're not going to show you examples of that. Well, I'll show you some examples coming up. So, goniophotography. So, as you can see here, a rotating mirror captures light from 3 axes at 2.5 degree increments. Light travels 25 feet to the photodetector right here to simulate a point source. The computer converts the measured illuminance in lux from lux to intensity, candela. Okay. Remember, candela is a measurement of intensity and is simply one angle, if you will, of the totality of all the angles emanating from a light source. Okay? So the computer integrates intensity into luminous flux or lumens. That's a goniophotometer. That's one method. By the way, it's becoming outdated. But if you remember our example of a direct-indirect light source, that's what this diagram is showing you. It is telling you that here's the 90-degree plane, right? The horizontal plane. And let's say that the light source is right in here. This is the amount of light that's coming up. This is the amount of light coming down. And all along these different degrees or angles, if you will, okay, there's different candela readings. That's very important to us. Remember what I told you about the 45 to 65 degree glare angles? If we count the number of candelas present in that 45 to 65 degree range, we can determine as a percentage of the whole how much that candela represents. And as a result, we can predict what the glare value might be of the fixture itself. Okay? Here are the 3 angles here. So we're measuring all across. Do I ask you to do this in class? No. Does anybody in my company even know about what this chart is? A few do. But for the most part, they're not too concerned about it. Because all they care about is, hey, how many fixtures do I need to light this room properly to 50-foot candles? That's the question that they ask. How do we calculate that? That's the important thing. Well, the computer will give us the information. All right. So here's another example of a roadway area or an area luminaire. And you can see here, the luminaire is here. Here's how much stuff is in the back, how much information is in the front, and on how far away from the source, which is right here, to the sides. That gives us all those distribution patterns. So what we're doing is we're counting candelas in each direction. From that, we can do a mathematical calculation to tell you foot candles, lumens, candelas. This baby, the integrating sphere photometry, or the integrating sphere, if you will, is what we commonly use today to determine the effectiveness of a luminaire. And typically, you see here right in the center, it's used for LED type luminaires. Without going into too much detail, we put the luminaire right in the center, and then we measure on every single angle inside of that sphere what the intensity is. We come up with a plot. Is there going to be a test on what this all means? No. Don't worry about it. Just get the concept. Put a luminaire in the center of the sphere, measure the intensity all around the sphere. What that does is tell us what the lumen output of the luminaire is. Because we sum total all of the candelas and we have a conversion factor into lumens, and then lumens can be converted to foot candle if we apply distance factors. Because obviously, if you're 12 feet away from a luminaire, your foot candles are going to be different than if you're 8 foot candles, 8 feet away, right? We also, at the same time, can give you a color chart that tells you the gamut and all of the color functions. Gets pretty intense. You can't read that right now, neither can I. But all the data is there. It accounts for all the different points that we measured. Sum total of all of those. So this is a actual photometric report. Now, here's an interesting chart right here. So forget all of this other stuff. That's the aggregate total of all the measurements. But here is something real world that we could use, right? It tells us what the foot candle ratings would be at a distance from the luminaire. And as you can see, as we go down in feet, we get less and less foot candles. But we get a wider range. So the further we are, distance we are from the luminaire, the wider the range, but the less intense it's going to be. And that chart pretty much demonstrates that. Here's another chart. Remember, we're talking about a luminaire that has uplight and downlight now, like a pendant, which has an uplight component and a downlight component. And so we have to look at what's happening in both directions. So if we look at the downlight and we see here between 45 and 65 degrees, we sum total all of these candelas, and that's what this is, and we compare that to the total number of candelas, we can determine what a glare factor might be. Okay? But if we sum total all of the candelas, we can convert the candela number into a lumens number. So the fixture can be rated now in lumens. So you will see a fixture that says, oh, this is a 12,000 lumen fixture, or it's 8,000 lumen fixture. And typically with linear like this, with an up and down, they'll tell you lumens per foot up, lumens per foot down. We're going to talk about all of these factors in another minute or two, but we're going to talk about the coefficients of utilization. So, and this will appear on your cut sheet. We'll have an example of that. I believe I emailed that to you already. But if you go to the part that says coefficients of utilization, I want you to understand something. we need to be able to understand what the reflectance values of the walls, the ceilings, and the floor. So in this particular case, we have divided this into 1, 2, 3, 4, 5 different zones. And basically, in this particular zone, we have a ceiling reflectance of 80%. Okay? And we can choose which column we're going to use depending upon what the wall reflectance is, 70, 50, 30, 10. But in order to do that, we can pick the column, but now we have to figure out which 1 through 0 through 10, the room cavity ratio. Okay, and I'll show you how to do that in a little bit. The room cavity ratio is important. We keep the floor reflectance at 20% for this chart. The computer will allow us to change the floor reflectance to any value we want. In a manual calculation, we use 20% reflectance off the floor as the default. Put that to the side. Spacing criteria. So we're looking at how far apart should we place these luminaires, right? It's a legitimate question. We have a downlight, a circular downlight, or even a 2x2 down a hallway. One of the common questions anybody will ask you is, well, how many fixtures do I need? How far apart should I be spaced? Okay, and there's a manual calculation that we could do. And it basically says S is equal to or less than SC times MH. Mounting height, okay, is important. Spacing criteria is a helpful metric for designing along with uniform luminance along the calculation plane. The greater the distance between the luminaire and calculation planes, the greater the spacing allowance. The spacing criteria does not indicate whether the illuminance will be appropriate, only that it will be uniform. The formula determines the maximum spacing for uniform illumination, not the optimum spacing, which depends upon desired illuminance and architectural considerations. Okay? All right, so you're not required in this course to do the spacing calculation. But as you can see here, this example shows you what would happen if we space the thing too far apart. See the one on the left, we have more even illumination, whereas the one behind them will have hot spots and dark spots. Even field angles are determined mathematically. Maximum intensity is 625 candelas. As you can see here, let me just see here. What is that here? Mean angle, 50% of maximum intensity. So at 42 degrees, which they don't really give you, they give you 40 and 45. It's 80 times 2 is equal to 84. Field angle is 10% of maximum intensity, or 66 degrees times 2, 132 degrees. I'm losing you here because basically what they're trying to tell you is that there is a physical calculation for how far apart fixtures can be spaced based upon the beam angle. That's the sum total. So it's very nice that they supply us with all of these numbers, but basically beam angle, 50% of maximum intensity, and maximum intensity in this case is 625, which is not even It's right at the top of the chart. Sorry, I missed that. Beam angle, 50% of 625 or 42 times 2 is equal to 84 degrees. Field angle, 10% of maximum intensity. 10% of maximum intensity is 62.5. Rounded it to 66 times 2 is 132 degrees. So once we know the number of degrees, we can determine how far apart these fixtures are. Nobody does this. Okay? I want to make that clear. Who's ever watching this? Nobody does this. Let the computer do it. Now, here's a technique known as scalloping. Two schools of thought. One says scalloping is good. It's architecturally interesting. The other school of thought says this is a really poor design. Okay? So depending upon which school you come from, and I come from the school that says this sucks. I like even illumination across that wall. This hot spot, low spot thing doesn't work for me. But that's a subjective observation. Somebody will look at that and go, oh, how interesting, what a nice pattern. You have to know your audience. We covered this already. This is the TM30 report. Again, we have 99 color bars in there, and we evaluate how close they are to a perfect circle. And as you can see here, this is a pretty good design because we have very little deviation from the perfect circle. That gives you some insight as to the qualitative aspect of the luminaire itself. The further away we drift this red line from the black line, the worse the quality of the light is. The less accurate the light is in terms of rendering color. The role of light calculation is to predict light outcomes. What outcome does this design produce? What design produces this outcome? More simply stated, what outcome does this design produce? How many foot candles am I going to get? Or how many luminaires do I need to create 50 foot candles or some other factor that we want to achieve? It's a quick estimate. We can get a detailed analysis from it, and then we can communicate that thought to the principals that are required to make a decision on the design. So, two methods: calculating average illuminance, the lumen method, which is manual; understanding one luminaire and aiming angles, point method, which I'm showing you up there. And it's effective for assumptions. It's kind of like the back of the napkin kind of, have you ever heard that phrase, back of the napkin? Basically, two people sit in a coffee shop and they sketch out something on the back of a napkin. It's a preliminary thought. It's not designed to be the absolute answer to the question. It's something that we want to test out to see if it fits within our concept. Okay, computer modeling is a whole other story. It gives us much more detailed information. It gives us 3D calculations and visuals for communicating with others, and it has accuracy and granularity. And so we're able to do a lot more things with computer modeling than we are with the manual methods that we're going to discuss today. Computer modeling is what we need to understand. So, the point method will require trigonometry. It will require employing the inverse square law. Everybody know what that is? Inverse square law. The further you get away from the source of the light, the less light's going to come out of it, and it's the square of the distance. So we will show you that in a second or two. We need to make horizontal calculations. We need to make angle calculations. And I've shown you on that chart there those three or pre-calculated tables. We can demonstrate that as well. But for the time being, simplified this. Okay. Because what you have in front of you is the chart we're going to use. So, illuminance at a point varies. The foot candles here is different from the foot candles here. And the foot candles here would be different from the foot candles here or here. So those are the three choices that we have to make. And here is the formula. And it really gets down to this. I'm going to go over this in a second. They complicated this. But as you can see here, there's a cosine adjacent to the hypotenuse. Okay?
I've heard that word a long time.
Right. Those are the three formulas that are represented on the chart that I have for you. So here's what we're going to do. In this exercise, we are going to solve for foot candles in the first box. Okay? You have a pencil? All right. So let's do this together. Solve for foot candles when the candle power is 6,000 and the distance is 10 feet. That would be this. Notice how the formula E is equal to I divided by D2. All right. So, foot candles equals, E is equal to foot candles. Okay? I is equal to candle power. And we're going to put 6,000 in that box. And we're going to put 10 times 10 in the bottom box. So, right here, you're going to put 6,000. And here, you're going to put 10 times 10 or 100. Right? So divide 6,000 by 100. What do you get?
I'm guessing 60.
Correct.
Oh!
Pretty damn simple. Now, it gets more complicated. Because the next one is this guy right here. Now we're going to put the candle power is 6,000. The distance is 10, but the angle is now 45 degrees. And so we have to multiply the candle power, 6,000, divided by 100. It's the same thing, but now we're going to multiply that by the cosine of theta. And if we know that the angle is 45 degrees, what is the cosine of theta? Well, I sent you the cosine chart. If we go back here, cosine of theta is 0.707. calculator at 45 degrees is 0.707. So multiply 60 times 0.707. What do you get? Siri, how much is 60 times 0.707?
42.42.
There you go. 42?
Yeah, 42.42.
That is correct. You got 2 out of 3 now.
So that's trigonometry.
Scary, isn't it? Third function. This guy right here. Solve for foot candles when the candle power is 6,000. The distance is 10 feet. And the angle is 30 degrees. Now we need to use the sine of 30 degrees. Hey Siri, what is the sine of 30 degrees?
The sine of 30 degrees is 1/2.
0.5. So what's our answer?
60 times 0.5, would that be like cut in half again? No. 60 times
60 times 0.5 is what?
30.
30. So 30. This one was 42. And this is 60. Congratulations, Sri. You got a 10 out of 10 on the quiz.
So, 0.5 is the angle of 30. And 0.707 is the angle of 45.
Yep. So sine and cosine come into play when the beam angle is not perpendicular to the object. And there you see the variation. We just did a calculation expecting the most intense light would be directly underneath the light source. As we move away from the light source, the foot candle levels drop. And if we start to introduce a severe angle on a vertical surface, the foot candle levels drop even more. We kept in this example the distance as the same, 10 feet. I did that deliberately. Okay? I also kept the candle power deliberately the same in this example. Why? Because I wanted to demonstrate that if we keep the distance constant and we keep we vary just the beam angle, but we keep the intensity of the luminaire the same, then we will get, this is something that we can compare accurately. If I started screwing around with you and putting different parameters in there, you wouldn't be able to appreciate the fact of what's happening here.
If the distance was 15 feet, it would be 15 times 15.
I'm sorry, there's
If the distance was, instead of 10, it'd be 15. Would it be 15 times 15?
right, 225. You can see how that would change. Are you with me on this?
Yeah.
Pretty easy. Pretty easy. These slides just reinforce what we just talked about. specifically when it's a downlight, and they have different beam spreads, right? So many manufacturers will give you an option on what kind of beam spread you might have coming out of their downlight. And in order for us to accurately predict, we could go through this manual calculation, or they could just do it for us. And that's basically what this chart is. It basically says, if 0 degrees aiming angle or directly down, here's the foot candle levels at 5 feet, 7.6 feet, 10 feet, and 12.5 feet. So as you can see, we go from 638 foot candles at 5 feet to 103 foot candles. That's the inverse square rule. As we get further away from the source, we square the distance, and we notice that there's a dramatic effect. There's only 2.5 feet difference between here and here, but look at the drop-off. So the inverse square rule takes place in all of these calculations, by the way. And so if we're aiming at a 30-degree angle or aiming at a 60-degree angle, here are all the calculations. So 3 feet, 4 feet, 5 feet, okay? And here are the 3 different beam spreads, 14 degrees, 16 degrees, and 22 degrees, and you compare all of them. We can basically make a decision on how many luminaires we need based upon a chart like this, couldn't we? Notice here, it actually gives you the dimensions of the circle of light. It's not a circle all the time. Sometimes it's an oval. All right? I'd rather use a computer. Guess what? We do. So, here's the review. The point method estimates the luminance at a point from one luminaire. The fundamental concept is the inverse square law, which I just demonstrated to you. Okay? Calculation inputs, you need the intensity of the source and the direction of the target, you need the distance to the target, and you need the angle of the beam to the target, and that is represented as theta. Okay? And these are the 3 primary formula that you will need to do these calculations. You now have a permanent record, both electronically, which I sent to you, and now you have a filled out version of that. Calculations are way more intense. We go from a concept. Here we have a school classroom, right? It could be a library, but it's not. Excuse me. And we have to determine the size of the room, the coefficient of utilization, which we'll talk about, the room cavity ratio, what light loss factors might be involved, and then we can generate either one of 2 things. We can generate the number of luminaires needed for our concept foot candles. And the concept sometimes is by law that says in the state of Connecticut you must provide 50 foot candles in a classroom. That may be something that's generally accepted. The authority having jurisdiction, if you remember that, they may say 50 foot candles in the classroom, deliver it. Well, how many luminaires do I need to deliver 50 foot candles? Right? That's one question. If I have nine luminaires in the build in this room, how many expected foot candles could I have? So one of those 2 questions has to be satisfied, and we needed to have a mathematical calculation to determine one of the 2, or both. And that's what we're going to do next. Now, in a room, we have to consider several factors. Number one, we have to consider what the work plane is. Where is this activity going to be measured? Is it going to be measured at the floor, or is it going to be measured at the work plane? What is the height of a work plane?
The table?
Yeah, what's that height? What is the average height of a work plane? 30 inches. 2.5 feet. Okay? So that's what's represented here. Now, as you can see, we have top of the room, this is here, but the luminaire may be dropped down below the top of the room. Okay? So the distance between here is what we need to calculate, right? So the lumen method estimates the average maintained illuminance on the work plane, or it predicts the number of luminaires needed to achieve a desired illuminance. One of those two things has to be solved for. How much light from the luminaires is absorbed, or absorption by room surfaces or degraded over time? So if you are in the middle of a factory and you're producing products that create dust, that will have an effect on the luminaire itself. So illuminance is equal to the density of luminous flux on the surface divided by the area. Okay, that's the definition of illuminance. Lumens per square foot. Now, holy crap, that looks complicated. So, E equals the average maintained illuminance on the work plane. That's what we're solving for. How many foot candles do we need on the work plane? Okay. Iota to total system lumen output. In order to do that, we need the coefficient of utilization. We'll get into that. We need to know what the light loss factor might be, and we need to know the area of the work plane. That's our formula. We're going to figure that out. That is figured out here. So here are the constraints to our model. Radiative flux transfer model can only be used in interior enclosed spaces. The length to width ratio has to be less than 1.6 to 1. Okay? If it exceeds that, then our model is not going to be accurate. All right? We have to have diffuse room surface reflectance. So if we were in a mirrored ceiling, for example, that wouldn't work. And the luminaires have to be evenly spaced, okay, which in this room it is. And we can only use one luminaire type. When we get to the software version, which is next week's class, okay, we're going to be able to inject multiple luminaires in the same space. And we're not taking into consideration furniture or partitions. But the software can. So as you can see, nobody does this manual calculation stuff. But we need to understand the basis of it because the computer's doing it in a lot more intense environment. The coefficient of utilization is the ratio of lumens arriving on the work plane to the total lumens of the luminaire. So let's say we have a luminaire that produces 1,000 lumens. how many lumens is arriving on the work plane? Gotta figure that out. That calculation is based upon interreflection, or, that's a fancy term for multiple reflections from all surfaces. So basically we're saying, if I want to know how much light is on the work plane surface, I have to take into account that light is going to come from the fixture down on the surface, but it's also going to bounce off the wall, bounce off the carpet and the floor, and then all those combined angles throughout the room will contribute to how much light is on the work plane. We have to take into all that. Coefficient of utilization does not depend on the lumens from the source or the luminaire. It does not worry about the light source or the luminaire efficacy. It only is concerned what the quantity of it is. And it doesn't care about color. 35K, 40K, 50K, whatever, don't care. Manual calculation. In the computer simulation, we will consider. So, here are your coefficients of utilization. This is the coefficients of utilization chart, if you will. And I explained to you this before. So let's just take, for example, the first section here. We have a ceiling reflectance value of 80%. That's rho. That letter that looks like a P, that's really reflectance, so it's 80%. And then we get to choose 70, 50, 30, or 10 reflectance off the walls. What determines that? The paint color, right? Or if we have wallpaper with bold colors or muted colors, it depends. So we're going to have to figure out the ceiling and the wall. Okay, if we say that the ceiling is 80% and the wall is 70%, we're going to hold constant the floor reflectance of 20%, which leads us into this column here. Got that? 80, 70 here. Now all we have to do is figure out the room cavity ratio. The room cavity ratio is essentially an aspect ratio of the vertical surface to the horizontal surface. The greater the height in relation to the floor dimensions, the greater the light loss from absorption of the walls. Height matters in this case. Now that is the formula for the room cavity ratio. We take 5 times the height times the sum of the length plus the width, and we divide that total by the length times the width. It's all in front of you. It's all laid out for you right there. You don't have to do a whole lot of thinking about it. But we have to understand, okay, that we're talking about this area here, the room cavity. Okay, if the luminaire was up here, then the room cavity would be the exact height, distance between the calculation plane and the top of the room. But in this particular case, we have to subtract this area up here because the luminaire is below the ceiling plane. So that's your room cavity ratio. The manufacturer show room cavity ratios from 1 to 10. Rooms with high RCRs absorb more light than those with low RCRs. And the RCR of 10 is a cube to the work plane force, which absorbs more light than rooms with a lower RCR. Okay. Here are the reflectance values that we talked about. common terms. So if we have a ceiling with white paint or plain plasterboard, we would have a ceiling reflectance value of 0.8 or 80%. Again, with walls, we would have white paint or plasterboard, that would also be 80%. And here are all the different other common building materials and the reflectance values. So we can create a chart that fits any one of these scenarios. And then here again is the ceiling. If you know, I mean the floor. And if you notice here, we're using a dark floor as opposed to a white floor. I don't know how many people have white floors. They used to have white shag carpets at one time. They were in vogue at once. They're not in vogue anymore. It's the last time I saw a white carpet. It's hard to keep a white carpet clean. The white would drive you crazy. Okay. So what's our object here? We got to find a room cavity ratio so we can locate in one of these columns foot candles, right? Notice as the reflectance percentages go down, so do the foot candle values. So we're going to do an exercise here. They did it, and they made it mysterious, and so I don't like it. So we're going to do it ourselves with our own numbers. Okay, so I'm going to read this to you so we have an example at least. Okay, so to ensure an understanding of how to read a coefficient of utilization table, assume the room cavity ratio is 3, and the ceiling reflectance is 70%, and the wall reflectance is 50%. So room cavity ratio 3, so we're in this horizontal section. What did they say the ceiling was? Ceiling reflectance is 70 and wall reflectance is 50. So ceiling reflectance is 70 and wall reflectance is 50. So it would be this column here. Because the room cavity ratio is 3, we would expect 93 foot candles. You with me? See how that works? Let's do another one. I'll just make one up, okay? Suppose we have a dark ceiling, 50% reflectance, okay? And we have a wall reflectance of 50. That would land us in this column here. And if we had a room cavity ratio of 5, we would expect 78 foot candles. Right? Because you're going from room cavity ratio over to this column here. That's the way we read that. Now, if you look at this chart here, we're going to use one of these. But before we do that, there are other factors to consider. So, light source lumen depreciation, which is signified by LLD designation. Luminaire dirt depreciation. Room surface dirt depreciation, RSDD, and ambient temperature factor. So those are all of the light loss factors that be considered. So what we do is we multiply the LLD times the LDD times the RSDD. Now, sometimes the ambient temperature factor comes into play because a luminaire is measured at a specific temperature. So we say that we are looking at let's say that's a 3,000 luminaire, but that's measured at 72 degrees Fahrenheit. What happens if it operates at an ambient temperature of 82 degrees or 56 degrees? There's going to be a variation there.
So temperature depends, like heating temperature? Or...
Well, in our example, we're not going to use temperature at all, okay? I simplified it. I took this out. But it is something that sometimes has to be considered, okay? And so we can alter the total light loss factor if we know all of these factors. Now, in the example that we're going to demonstrate today, we are going to be able to tell you what these factors are. I sent you a chart. And the chart actually will predict, based upon the environmental conditions, what the dirt depreciation might be for a particular environment. So in a clean room, there's very little dirt depreciation. In a classroom, we have a little bit higher, and depending upon how much dust is collected by a wood floor or a carpet floor, will determine and alter this.
So we have to calculate the carpet and the floor and what material it has.
Right, but typically what we'll do is we'll lump all of these together and come up with a number. Okay, and I will discuss that as we go through this. So I gathered with in fact, you might want to just tell you what we did in this market. So I have competitors. There's 4 of me here, representing the 4 biggest lighting manufacturers. Okay, each one of them has a person in my position, and we had a meeting on it, and we said, look, we're all producing photometric reports. Why don't we all agree on what the dirt depreciation factor might be, or the total depreciation factor might be, so we're all using the same calculation and nobody's cheating. And we determined that the actual factor that we were all going to use is 0.9 or 90%, 10% degradation over time, right? But in today's exercise, I'm going to give you all of these values. The lumen method estimates the average horizontal illuminance. Horizontal, not dealing with vertical. So luminance factor is luminous flux reaching the surface divided by the area. That's foot candles. Okay? Luminous flux divided by area, foot candles. So the calculation inputs we need are the room cavity ratio and reflectances. The luminaire lumens or lamp lumens, we're going to use a fluorescent fixture as the example in this exercise. And the coefficient of utilization, we're going to have to figure out what the light loss factors are. So the limitations is a regular luminaire array of one type, diffuse surfaces,